Hello everyone. Today we are going to discuss a new topic from heat and mass transfer, and the topic is radiative heat transfer. Okay, so this topic is from the 5th module, and I'll be using the textbook Fundamentals of Heat and Mass Transfer by Incorpora, and I've used some video lectures also, which is from IIT Madras. Okay, video lectures of Professor Balaji from IIT Madras. Okay, now radiation heat transfer. Okay, so we'll start with radiation heat transfer. Okay, so as we know that radiation heat transfer is actually one of the three modes of heat transfers, and usually I used to say that there are only main two modes of heat transfer. Anyway, this is one of the main modes of heat transfer. Okay, the other two modes which we have already learned is the conductive heat transfer and the convection heat transfer. And convection is basically conduction plus bulk fluid motion, so you don't typically call it as a mode of heat transfer, but yeah, in normal terms we can see it as a mode of heat transfer, a form of heat transfer. Okay, now the major difference between the conductive heat transfer and convective heat transfer and the radiative heat transfer is that in the case of radiation heat transfer you don't need any medium for the transfer of heat. Okay, so if you take a typical example, the radiation heat exchange between sun and earth. Okay, sun and earth. So you can see that every day in the morning to evening we receive heat energy from sun, and we know that there is a lot of space between the sun and earth where there is no medium at all. Okay, there is no medium at all. So how does this get transferred? How does the heat reaches earth? So this is a typical example that the radiation heat transfer does not require any kind of medium, because most of the space between sun and the earth is vacuum. Okay, since it is vacuum, there is no medium in between, and this is a typical example which shows that there is no requirement of a medium for radiation heat transfer to take place. Okay, so that is a major difference between the conductive heat transfer, convective heat transfer, and the radiative heat transfer. Now let us see the different types of heat transfer, like how does radiation heat transfer take place in the case of a solid, liquid, and gases. Okay, so first of all let us see the case of a solid or a liquid. Okay, so when a solid and a liquid, okay, so in the case of a solid and liquid, if you look at this picture, so if it is a solid or liquid, this radiation, like if you take the case where a solid or the heat from a solid or liquid is emitted to the gas or vacuum. Okay, so if you look at this thing, this can be seen as a surface phenomenon. That is because in the case of a solid and liquid, we consider that whatever molecule is there inside this, if this molecule emits some radiation, some kind of radiation, then the nearby molecule will absorb that radiation. Okay, because it is closely packed. Since it is closely packed and the molecules are not in random motion, just like the gases, just like the case of gases. In the case of gases it is different, because the molecules are actually far away from each other, but here the molecules are not that far away from each other, which means that the radiation that comes out of one molecule can be absorbed by the other molecule. So in effect we say that the interior, the radiation from the inside part of the solid or liquid is actually absorbed by the molecules itself, which means that the radiation to the surface is not a volume phenomenon, it is a surface phenomenon. The radiation heat transfer is a surface phenomenon in the case of solid and liquid. But in the case of gases, there is a little bit difference. In the case of gases, you can see that if you bring in a figure, so if you look at this figure, the figure is actually coming in. So this figure, if you look at this figure, you can see that the gases are actually, in the case of gases, the molecules are actually a bit, there is a gap between the molecules, right? So since there is a gap between the molecules, and there is no typical surface for the gas. Like you can't say that okay, surface of a gas, there is no surface of a gas, because the gas will actually occupy all the space that is available. So you don't have a surface for the gas, and you can't have an exposed surface because there is no exposed surface. The gas will expand. If you expose the surface, then the gas will expand through that. So basically the heat transfer actually happens inside the gas through the as a volume phenomenon itself. So it happens as a volume phenomenon. In this case, the molecules are actually moving at some speed, at a higher speed, and moving more freely than that of the solids and gases. So the molecules will emit radiations, and they will carry radiations with it, and then it becomes a volume phenomenon. Okay. Now, in usually we say that for low temperatures, like whenever we consider the heat transfer from any plate or something of the hot plate or something like that, we used to neglect radiation heat transfer. There are many people who actually say that okay, radiation heat transfer, generally we say that radiation heat transfer, oh, that is not much effect, there is no much effect due to the radiation heat transfer. Let us see a typical case. Let us make a case study and see whether radiation heat transfer is of much important as far as any analysis is concerned. Okay, so if I take let us assume that I have a metal block. Okay, if I have a metal block here, then let us say it is kept at some 80 degrees Celsius. So this is at 80 degrees Celsius. So 80 degrees Celsius is somewhat like 353 Kelvin or 353 Kelvin. One of the most important thing as far as radiation heat transfer is concerned, we always take this temperature in Kelvin. Okay, the temperature is not taken in degrees Celsius as far as the radiation is concerned, because the typical equation for radiation is T raised to 4 minus T raised to 4. Okay, so there is a non-linearity in this, and T to the power 4, T to the power 4 is there. That is the reason why we should take in Kelvin. Okay, we'll come to that later on. So let us assume that this plate is at 80 degrees Celsius for the time being, and then the surrounding is at, let us say, T infinity, which is equal to some 30 degrees Celsius or 303 Kelvin. Okay, we'll see what emissivity is, but for the time being let us assume that the emissivity of this is equal to 0.9. I'll explain what is emissivity, and the length is equal to let us say 0.5 meters. Okay, so if you have, okay, I'll just erase that because we need to draw something there. So emissivity is equal to 0.9 there. Now let us assume that this is actually suspended in still air. This is at 80 degrees Celsius and the air is at 303 Kelvin, but it is still air. So what is the predominant mode of heat transfer? And like in still air, when a hot plate is actually suspended in still air, we assume that the predominant mode of heat transfer is actually free convection. Okay, now let us see whether free convection is the only predominant mode of heat transfer, whether radiation heat transfer actually whether it is important or not. Okay, then so the free convection heat transfer, if you draw the boundary layer for free convection heat transfer, you can see that there is something like that. The boundary layer is something like that, and there is the velocity profile will be somewhat like this. Okay, so this is the velocity profile in the case of a free convection boundary layer. And as you have seen before, one of the correlations to find out this free convection heat transfer, heat flux in the case of a free convection heat transfer, is actually Q flux equal to H delta T. Okay, so H delta T, Q heat flux will be equal to H delta T, where H is the let us assume that that is the average convective heat transfer coefficient, and delta T is the difference between the temperature, that is 353 minus 303 Kelvin. So in the case of convective heat transfer, even if it is 353 minus 303 or 80 minus 30, you will get the same answer, that is 50 degrees Celsius, or 50. Delta T will be 50. Now in order to find out the value of H, we use the next formula, that is Nusselt number is equal to HL over K. Okay, here we know the value of L, and let us assume that and we can, for using the tables and everything, we can find the value of K. Okay, L is 0.5 and we'll find out the value of H. Let us say H is the average value. I'll give the bar for the average value. So Nusselt number is equal to HL by K. In the case of free convection heat transfer, we have another correlation, that's Nusselt number is equal to 0.59 Rayleigh number raised to 0.25. Okay, so this correlation is given by Sparrow and Gray. So that is Sparrow and Gray. Okay, so this correlation is given by Sparrow and Gray. And if we find out the Rayleigh number, then you can find out the Nusselt number, and from that we can find out the H, and using that H you can find out the value of the heat flux. So that is how we actually solve for the convective heat transfer problems. Even if it is convective heat transfer or free convection heat transfer, we actually solve for that. Now what is this Rayleigh number? Rayleigh number is actually Grashof number times the Prandtl number. So Ra is actually Grashof number times the Prandtl number. Okay, and for steel layer we take the Prandtl value of Prandtl number as, let us assume that the Prandtl number is equal to 0.71. Okay, usually from all the properties of air we find that the Prandtl number for these kind of temperature ranges is around 0.71. Okay, now what is the Grashof number and what is the Prandtl number? Okay, the Grashof number is given by G beta delta T L cube over, we have seen all these things in the previous chapters. Nu, okay, this is not V, this is nu square, and the Prandtl number is actually nu over alpha. Okay, so that's a viscosity, and this is alpha, the Prandtl number. Okay, now G is the acceleration due to gravity, G beta, okay, not B, G beta. Okay, so G is equal to 9.81 meter per second square, which is the acceleration due to gravity. Beta is the thermal expansion coefficient, which is equal to 1 over T mean. Okay, T mean is the mean of the temperature, in this case that mean of the two temperatures. So T mean is actually equal to T, let us say, plus T infinity over 2. Okay, so T plus T infinity over 2 in this case, if you calculate that, we get the T mean is equal to, this will be equal to 303 plus, or 353. So if I take that one first, I'll write 353. So that is 353 plus 303 over 2. Okay, so you get the value I have calculated, that is 328 Kelvin. Okay, so that is the value of this thing. So you get beta, T mean is that, so you get beta will be equal to, so what is the value of beta from this? Okay, I've calculated the value of beta, and that is 0.03 times 9.8 times 50. Okay, fine. Now that is 0.003. Fine, 0.003, because that is 1 over 328, so that you get it as 0.003. Okay, it's equal to 0.003. Fine. Then delta T is something that you know. Delta T is actually equal to 50, and L is 0.5 meters. Delta T is 50 Kelvin, 0.5 Kelvin, sorry, 50 Kelvin, and this is 0.5 meter. The Prandtl number is given by 0.7. You get this value from the properties table, and then if you take the next value, that is the nu is equal to, now for air, nu is equal to 16 times 10 to the negative 6 meter square per second. So if you plug in all these values into the equation for the Rayleigh number, you get the value of Rayleigh number. Ra will be equal to, what can you say, 9.8 times 0.003 times 0.5 cube times 50 times 0.71 over the whole thing divided by 1.6 times 10 to the negative 6. Okay, oh sorry, not 1.6, 16 times 10 to the negative 6, sorry. Okay, that is 16 times. Okay, so that is 16 times 10 to the negative 6. So this value, I've calculated that and I've got the value of 5.096 times 10 to the 8. Okay, so that is a Rayleigh number. Now we can use this Rayleigh number and try to find out the Nusselt number. So we can see that the Nusselt number from Rayleigh number, Nusselt number will be equal to 0.59 times Rayleigh number raised to 0.25, and you get that's equal to, you use the 5.096, and that will be equal to 88.64. okay, and from the property tables you can see that the thermal conductivity K will be equal to 0.03 watts per meter Kelvin. Okay, so H is given by, from the correlation for Nusselt number, H is given by H equal to Nusselt number times K over L. Okay, so if we use this correlation, we can see that the value of H is 5.32. okay, when you calculate this you get this, so which is equal to 5.32. okay, now you take this value and the Q prime convection will be equal to H delta T, this is watts per meter square Kelvin, the unit for that. H delta T, that's equal to 5.32 times 50, that is equal to 266 watts per meter square. Okay, so this is the value for Q convection. Now let us find out the value for the Q radiation in this case. Okay, so Q radiation is actually equal to epsilon sigma T raised to 4 minus T infinity raised to the power of 4. So this value, if I take this, we have assumed that the emissivity is 0.9. we'll see what emissivity is later on times, and sigma is the Stefan-Boltzmann's constant, which is equal to 5.67 times 10 to the negative 8. This is very easy to remember because it is 5, 6, 7, 8, but you have to see know where how to give it. Okay, and there is a minus sign also, a negative sign is also there. So this is 354 3 to the power 4 minus 303 to the power 4. Okay, and you get this value as 357.76 watts per meter square. Now if you compare these two values, that is the Q radiation and Q convection, you can see that the Q radiation is actually higher than the flux, heat flux. Q radiation is actually higher than the Q convection. But that, and we have just considered 80 degrees Celsius. 80 degrees Celsius is not a very high temperature. When we are considering very high temperature, the Q radiation becomes more important because it is T to the power 4 minus T to the power 4, T ambient to the power 4. So if we have some 1000 Kelvin, then 1000 to the power 4 minus 303 to the power 4 becomes a huge value. Okay, so this is actually, so from this example itself we can see that even for temperatures of around 80 degrees Celsius, the radiation heat transfer is actually very important. So radiation cannot be neglected, just like we used to say that okay, radiation can be neglected, but usually radiation cannot be neglected. This example actually shows that. Now in the case of water and solid and all those things, in the case of water things will change because the convective heat transfer coefficient is actually much higher, and the conduction is actually much higher when compared to the gas. And the gas in still air, you saw it as 0.03 watts per meter Kelvin, and for water it is around 0.5 or zero point 0.6. okay, it is about around 0.6, which is much higher. So when it becomes 0.6, the convective heat transfer is actually much higher. Okay, so it depends on the medium also. Generally we cannot neglect radiation heat transfer. Okay, having said that, we'll continue with the radiation heat transfer. And now we know that radiation, there are two theories in which how the radiation is actually propagated. Okay, one theory says that radiation is propagated as particles, okay, as small particles, or which is called as photons or quanta. Okay, so propagation of radiation, okay, so one theory says that it is photons, so small packets of energy, these photons, okay, this is actually small packets of energy or energy quanta. Okay, now that is one theory, and this theory is actually used in many cases, like the description of black body and analysis of heat transfer in the case of a black body. Now the second theory says that radiation is actually electromagnetic waves. Okay, electromagnetic waves. Okay, now for the time being we will be concentrating more on the electromagnetic waves, that form of radiation, and then when we consider the black body radiation, we will consider the other form also. So electromagnetic waves. Now the propagation of electromagnetic waves, we know that there is an equation, that is the wavelength of the wave will be equal to c over v. Okay, so the c over v, where c is the speed of light in the medium. Okay, so the c is actually speed of light in the medium. And usually if you are concerned the sun and earth and all those things, the celestial bodies, we usually take c naught, which is actually equal to 2.99 times 10 to the 8 meter per second. Okay, so this is c equal to 2.998 times 10 to the 8 meter per second in vacuum. Okay, now when you're considering the electromagnetic waves, we have to consider the electromagnetic spectrum. That is, in order to describe how the radiation wave take place, waveform of radiation actually takes place, we have to see in which part of the electromagnetic spectrum does the thermal radiation become important. Okay, so we know that there are so many different types of radiations and waves in the electromagnetic spectrum. I'll just bring the figure for that, so we can see that. Okay, so this is a typical electromagnetic spectrum. So if you go through these things, you can see that there are gamma rays, there are X-rays, there are ultraviolet rays, then you have infrared and microwave, and in between these you have the visible waves also. Now if you see, the thermal radiation actually lies between the wavelengths of 10 to the power -1 to the 10 to the power of 2 micrometers. Okay, so the wavelength is actually 10 to the power -1 to 10 to the power 2 micrometers. All the other radiations doesn't come under thermal radiation. Okay, so under these conditions, that is from the wavelength 10 to the power -1 to 10 to the power 2, the radiations or the waves are actually, electromagnetic waves are actually affected by the temperature, and the temperature can make some difference in this waves also. The temperature can actually affect the waves. The temperature difference can affect if there is an increase in temperature or a decrease in temperature, that can actually affect these kind of the waves that actually come. It may affect the properties of the waves that come between 10 to the power -1 and 10 to the power 2. When you say 10 to the power -1, it has a small part of the UV radiations. It has a complete visible, and then it has a complete infrared radiations. Okay, so these are the different types of waves that actually or the part of the electromagnetic waves which actually comes under the thermal radiation. Okay, so we will actually now we will come to the remaining part of this in the next video. Okay, and we will